Chapter 12 Parameter Estimation. Next, let's see how parameter estimation is executed in logistic regression model. In logistic regression, the primary goal is to find the best values for the parameters that define the model. These parameters are the beta values in the logistic regression equation. In developing a logistic regression model, maximum likelihood estimation is used to estimate the parameters of a model. This statistical method is called MLE for short. In the context of logistic regression, MLE aims to find the parameter values beta that makes the observed data most probable. In MLE, the process of finding the best parameter values involves maximizing the likelihood function. In other words, MLE seeks to maximize the likelihood function. The likelihood function represents the probability of the observed data given a set of parameters. In logistic regression, it quantifies how likely it is to observe the given set of outputs from the inputs under current parameter estimates. For each data point, the logistic regression model predicts a probability of being in class 1. The likelihood function is the product of these probabilities for all data points. For those data points actually in class 1, we use the predicted probability directly. For those in class 0, we use 1 minus the predicted probability. MLE seeks to maximize this likelihood function. That is, it adjusts the parameters to make the observed data as probable as possible under the model. In practice, it's common to maximize the log of the likelihood function because it simplifies the calculations, turning products into sums. Let's understand the likelihood function in more detail. First, what does it exactly mean? The likelihood function in the context of logistic regression doesn't exactly quantify the probability of the output being in class 1 for a given set of input values. Rather, it quantifies how likely the observed set of outcome is, given a set of input values and a specific model defined by a set of parameters. In binary classification, the likelihood function quantifies the probability of outcomes considering both class 1 and class 0. Let's break down likelihood function further. L beta is the likelihood function. It tells us how likely our observed set of data is, given our current set of parameters. The big pi symbol means we multiply a bunch of terms together, one for each data point in our dataset. Probability yi equals 1 given xi is the probability that our model predicts for the ith data point being in class 1, given its features xi. 1 minus the probability of yi equals 1 given xi is the probability that our model predicts for the ith data point being in class 0, which is just 1 minus the probability of it being in class 1. Yi is the actual class of the ith data point, and it's either 0 or 1. So, let's see how likelihood function works. For each data point, if the actual class yi is 1, the first term of a likelihood function becomes the probability of yi equals 1 given x, and the second term becomes 0 because 1 minus yi equals 0. So, it becomes the probability of yi being 1 given xi. If the actual class yi is 0, the first term of the likelihood function becomes 1. and the second term becomes 1 minus the probability of yi being 1 given xi. So it becomes 1 minus the probability of yi being 1 given xi. We multiply these probabilities together for all data points, and that gives us the likelihood of observing our entire dataset given the parameters of our model. Let's look at some examples of likelihood calculations. Let's start by looking at the calculation of the likelihood for a single data point. Let us consider the case of a binary classification model to make a prediction about a certain dataset. Suppose there is a data point x1 and the observed value of label y is 0. Suppose that the model predicts that x1 has a probability of 0.6 that label 1 is 1. Let us compute the likelihood in this case. As we saw earlier, we can compute the likelihood by this formula. In the probability part of the first term, we assign the probability that y is 1 as predicted by the model. In the exponent part, yi is assigned the value 0, which is the observed value of the label. The probability part of the second term is 1 minus the probability that the label is 1, which is 1 minus 0.6, so it is 0.4. Substituting these into the formula, the likelihood is 0.4. Suppose the dataset consists of 5 data points, including x1. Calculate the likelihood for each data point in the same way. Then, multiply all the likelihoods for each data point. This is the likelihood of the model. The higher the value of the likelihood, the better the model explains the observed data. The likelihood of this model is 0.004. Among the data points, the cases with an observed value of 1 for the label, that is, positive cases, are x2 and x5. On the other hand, if the cutoff value of the prediction probability is 0.5, the cases that the model predicted as positive are x1, x2, and x3. Therefore, the model correctly predicted only data point x2, so the model's prediction accuracy is not high. Consider a case of another model applied to the same dataset. This model outputs a different predicted probability for each data point. Assuming a cutoff value of 0.5, this model correctly predicts 4 out of 5 data points. In other words, it has a higher prediction accuracy than the previous model. Let's compute the likelihood for this model as we did for the previous model. The calculation results show that the likelihood is higher than the previous model. The higher likelihood indicates that the prediction accuracy of the model is higher. Let's summarize the main points of this chapter. In logistic regression, the goal is to find the parameter values that maximize the likelihood function. A higher likelihood indicates the model better fits the observed data. In summary, the likelihood function in logistic regression is a measure of how probable the observed outcomes are under the model, given the input values and the current set of model parameters. It's not just about the probability of class 1 outcomes. It includes the probability of class 0 outcomes as well, and combines these across all observations.